Hello students, welcome to the course on mechanics of machining. This is the 10th lecture of this course. We have almost reached now midway. So today I am going to talk about mechanics of oblique cutting. Perhaps you may find that this is the toughest lecture of this course. Why? Because we are mostly discussing three-dimensional geometry, and you know that it is becoming very difficult to explain three-dimensional geometry by means of the blackboard or by means of a screen. However, we will try to get something in this hour. That there are some books on this, textbook of G.K. Lal's book on machining science can give you some information about the mechanics of oblique cutting, and you have to visualize a lot. You can make your own models, and after that you can understand that what is the oblique cutting mechanics. This you have to do by means of making some models. So let me just review again that concept of the oblique cutting. Here I have made a three-dimensional picture of the cutting process. There is a workpiece and tool is moving in the x direction. So x direction can be called as the cutting velocity direction. Now here in the orthogonal cutting edge is perpendicular to the x axis. That means it is perpendicular to the velocity direction. But in this figure, if you are seeing that the cutting edge is inclined at an angle from perpendicular direction. That means this is x direction. If the cutting edge would have been along y direction, then we would have said that it is a orthogonal machining, but in this case it is inclined at an angle I. This is called inclination angle, and as a result of that, when the cutting process is taking place, then the chip is also flowing at certain angle. It is not just at 90 degree to the cutting edge, it is on that plane, it is going in this direction. Cutting edge of the tool is inclined at an inclination angle I with normal to the cutting velocity vector. The chip generated flows on the rake face of the tool at an angle approximately equal to I with the normal to the cutting edge in the plane of the rake face. This is also one type of observation by Stabler that he found around 1950, that it is the chip which is flowing that is inclined at approximately equal to I. So suppose this angle is I and I draw a perpendicular to the cutting edge on this plane, then the chip flow will make angle I from here. Okay. So that means chip is going normally. Suppose you have, that is the cutting edge, then the chip 90 degree to this is this line, but chip does not flow like this, rather it gets inclined, and that inclination angle is I. Cutting edge extends beyond the width of the workpiece on either side, that we are assuming here that it is extending, so that we can understand that it is only shearing action. Cutting forces act along all three directions, that is along x, y and z axis. X direction also you have, that is called cutting force or power producing force, and then along y direction also and along z direction also. So this is cutting force is acting on all three directions. Whereas in orthogonal direction, if it is pure shearing operation, then there is no force along y direction. There is one force that is called cutting force, that is along x direction, and there is a thrust force that is along the z direction. So this, but here we have to get three components in a space, so you have to consider all these components and you have to do that complicated analysis. Before moving further, let me explain that some concept of the two rake angle. You see that rake face is inclined like this, and in the orthogonal cutting there is a rake face, and we say that there is a reference plane. That plane is making an angle of 90 degree from cutting velocity, that means cutting velocity direction is this, then reference plane is this, that means normal to the reference plane is nothing but the cutting velocity vector, and this is making an angle alpha from here. So, this is alpha, that is only one rake angle we define in orthogonal cutting, but in this case there can be several cutting rake angles that we have discussed in the previous classes also. We told about the normal rake angle, we told about orthogonal rake angle, we told about side rake angle in American standard system. So, here we are going to tell you something more, that here if you define, suppose you take one plane which is perpendicular to the cutting edge. Perpendicular to the cutting edge, if you make a plane, that plane will be called normal plane. Okay? Normal plane that need not be orthogonal to the reference plane. So, suppose you are making that one that is normal plane. On the normal plane, if you show that inclination of surface from the perpendicular to the cutting velocity, then that is called alpha n, that you already know, that means slope of this is alpha n. We can also have that one plane which will contain, which can contain that orthogonal, that is orthogonal plane, that which can contain the cutting velocity vector. At the same time it will be orthogonal to the reference plane, and in that plane we define orthogonal rake angle, or sometimes we call velocity rake angle. But in this I am going to show one more plane, that plane is containing the velocity vector v, and also it is containing the velocity, chip flow velocity Vc. So, V and Vc both are contained. You make a parallelogram like this, and in this if you show that this, and now you can see that in this plane that we are showing eta c is the chip flow angle we call, and in this one if I show the inclination of the surface on this plane, that is the, we say, two rake plane, in this if we show, then that is called two rake angle. So, you understand that what is a two rake angle, that it is going here and then it is making from its vertical that line here projection, this one it is making that alpha e. So, alpha e is called two rake angle, and many people believe that in fact two rake angle may give the better indication, it may be analogous to the rake of the orthogonal system. So, here you have to understand that I again emphasize that you may think that in 3D how it goes. Usually suppose there is a sloping surface, let us say that AB is the sloping surface. If I say that find out the slope of this surface, you know it is very easy, you know that how much it is sloping. When you are moving B to A in this direction, then how much you are lifting up vertically, that means this height may be h, and how much you are going in the base direction. So, we say this angle tan alpha is equal to h by b, that is how we do, and we talk about only one slope. But suppose think about the three dimensional case. In that case, suppose the surface is like this, I am designating, that means this is a road, I have shown that isometric type of view. Now, you are moving on the surface. If you are moving on this parallel to this, that means so that your parallel to the vertical plane, then of course that your slope is h by b only. But suppose you are on this plane, you are moving from this point to this point, then slope is what? It is 0, because you are going from here to here, vertically you are not lifting up. So, that surface is inclined in this direction, but the surface is not inclined in the other direction. Similarly, you can think that suppose you are moving from here to here like this diagonally type thing, then your slope will become different. So, the slope will depend on in which plane you are measuring. Suppose I cut a vertical plane cross section, then you get that what you make in the diagram in the books in solving mechanics problem, you just simply make a slope or something like that. But if you make a horizontal cut, you get a different one. So similarly, you can here also you have to see this, that you have to visualize this one, that here you are having alpha n normal rake angle in the normal one, but I am now talking about this plane which is containing the chip velocity and it is also containing the tool velocity, and in that particular plane what is the slope? If there is O and B, 2 points are there, so how this O and B, when I am going from O to B, then how much I am going from in the horizontal direction and how much I am going in the vertical direction, like that. So this is alpha E, and this one, so in the oblique cutting process, the tool cutting edge is inclined at an angle other than 90 degree to the direction of cutting velocity vector. The mechanics involved in the process have not been investigated to the same extent as the simple orthogonal cutting process, because that is obviously difficult. Merchant in 1944 he proposed a model for the first time. Other researchers are Stabler in 1955, whom I was talking, that he gave that relation that chip flow angle eta c is equal to the inclination angle. That chip flow angle eta c, that will be equal to the inclination angle that he observed. Later on he said that it may be equal to 0.9 I. That means chip flow angle may be 0.9 times this thing, but more or less you can say it is 1. And Brown and Almara in 1964 also did, Spans 1967, 1970, and then Marcos in 1972 have done this type of analysis. Now normal rake angle is a, usually many authors believe that normal rake angle is a fundamental variable influencing the forces and shear angle. They think that it is better to take the normal rake angle. In fact, you take that normal rake angle because there is one paper published in 1967 in SME journal. Here it is stated also that we make to apply the oblique cutting, the results of the large amount of orthogonal cutting data available, it is necessary to select a rake angle in oblique cutting which corresponds to the unique rake angle of orthogonal cutting. Now previous investigators are at odds as to which rake angle, alpha n, that is normal rake angle, alpha v, velocity rake angle or orthogonal rake angle, or alpha e, that means true rake angle, should be considered. That means there is a dispute among the researchers, there is no proper agreement. However, in recent work, Stabler shows that the power consumption in oblique cutting is directly proportional to normal rake angle. He thus concludes that the normal rake angle is the only fundamentally correct way of measuring rake. Experimental results by Brown and Almarego also suggest that alpha n is the controlling rake angle. So this is what that many persons have done like this. So you have to consider normal rake angle, and in that you can do the analysis similar to orthogonal type of analysis. In fact, once I have given some hint about that when we were solving the turning problem, but many people will believe that no true rake angle or effective rake angle alpha e should be taken. So rake angle can be measured in 3 different planes. The rake angles corresponding to these 3 planes are normal rake angle, velocity rake angle, that is orthogonal rake angle, and effective rake angle alpha e. Now these 3 angles are obviously related from the geometry, and these relationship can be obtained as this: tan alpha v is equal to tan alpha n divided by cos I, or tan alpha n is equal to cos I into tan alpha v. In fact, we have discussed this also in one class, that how it goes, that you know that this one again I can give some sort of hint, that suppose you have, it is something like this: tan alpha n is equal to tan alpha v into cos I. That means tan alpha in normal rake angle will be somewhat less and this will be more. So it is like this. So if we make some sort of that some sketch, then we can appreciate that thing, that you have some cutting edge like this, and there is a normal plane, that on that particular plane if you have got alpha n, this is alpha n, and this one is and this is something like vertical direction is this, and this may be the surface of that tool. So it is something like this. So in this there is a alpha n, this angle was suppose alpha n in normal angle, and that means suppose I make one sketch like this, one plane, I should show some orthogonal view. Suppose this is the vertical one, and suppose this was some line on that normal plane, and this is alpha n. So naturally alpha n becomes, tan alpha n becomes what? This divided by this vertical height. Now suppose you incline that plane to an angle I, suppose this inclines, so you have to take its projection. So in this case, this on that vertical height may remain same, but if you incline it by I, then this base may reduce by cos I factor. So that means base becomes cos I times the previous base and height remaining same. Therefore this tan alpha O will be tan alpha n divided by cos I. Similarly, you can find out that true rake angle will be sin alpha E is equal to sin I sin eta c plus cos I cos eta c into sin alpha n. Generally eta c is a chip flow angle, eta c is equal to sin I itself, and if we say that sin I is basically same sin, if I is 0, that means orthogonal cutting, in that case sin alpha E becomes sin alpha n, that means the velocity this true rake angle is nothing but the normal rake angle. Okay, that simply it goes like this, and in fact all three angles become same. So this relation was reported by Stabler first, and slowly you can derive if you make projections, and if you do that in a slow manner, then you can understand that how this is related. Maybe at the end of the lecture we may discuss a little bit more on this, but this relation you can note down, that sin alpha is equal to sin I sin eta c cos I cos eta c sin alpha n. Experiments show that the force in the direction of cutting velocity remains constant with normal rake angle. So again I am emphasizing the point that normal rake angle is more important, and the angle from the shear plane to the plane containing the newly formed work surface measured in a plane normal to the cutting edge is called the normal shear angle. You have known the shear angle. In 2D it was very easy for me to explain. It was like this, and it is simply this one, and I was telling that chip is flowing like this, and this angle was phi. All right, but it is in 2D there is only one plane, that is the plane of paper. But here I define normal shear angle, that is in a plane which is normal to the cutting edge. Same thing we are measuring in that plane, then it becomes phi n. And when the angle of shear plane is measured in the plane containing the cutting velocity Vw and the chip velocity Vc, that means the true plane, then the angle is called the effective shear angle. So we get effective shear angle also. And like in the orthogonal cutting, we can get these relations also. Normal shear angle phi n can be evaluated as tan phi n is equal to RT, which is the cutting ratio, into cos alpha n divided by 1 minus RT sin alpha n. This you can very well do that. And tan phi e can be likewise can be derived as Vc divided by Vw. Vw is the work velocity, and this is cos alpha e 1 minus Vc divided by Vw sin alpha e, and this can be Vc by Vw can be written as Rt by Rb. What is Rp by Rb? Rt into Rb. Rt is actually the chip thickness ratio. So Rt is equal to T divided by Tc, and the chip width ratio is Rb, RB is equal to B divided by BC. Okay. Usually in the orthogonal cutting, in Merchant's analysis, you assume that B was equal to BC. So RB was always 1. But in general, you may have some width also. So by incompressibility condition, that means what will have, that if we say that this one, that we will be having this type of relation, RT means T times B and VW, that means work velocity or something, and this is chip velocity TC times BC, and this will be VC, that means chip. So volume remains constant, no doubt, whether it is 2D machining or 3D machine, volume of the metal remains same. So what it gives me, that T by TC is RT. So that means this is T by TC. If I bring TC this side, then it will be RT, and B by BC is RB, RT, RB, and this is VW into is equal to VC. So therefore VC by VW is equal to RT and RB, right? So we can put this one, so we have put here like this, RT RB cos alpha e 1 minus RT RB and sin alpha e. This is has come extra is sin alpha e, and so incompressibility condition is giving me this. So this also is relation you have understood. Now in this case, I am again explaining the difference between orthogonal cutting and oblique cutting. Orthogonal cutting is like this, that cutting edge is at 90 degree to the velocity, this one V, this is workpiece is going like this, and in the oblique cutting, that cutting edge is inclined at an angle I, and this is 90 degree here, that 90 degree line is this. So velocity vector is making angle actually from here, okay, this is this one, and this chip is flowing like this. So I draw it here. So suppose normal to the cutting edge is this line, but the chip is flowing like this, that is chip flow angle. Many books are sometimes people define like this also, that this is orthogonal cutting, that the in lathe machine tool is moving like this, and they say if the tool is moving like this, this is orthogonal cutting, but it is actually it should not be correct definition. In fact, this type of turning operation is not orthogonal at all unless you are doing the machining of the tube, because here in orthogonal cutting another thing is that the edge, tool edge should extend beyond the job also. This should be, that should be, but many people say okay, this is pure orthogonal cutting and I will call this also as orthogonal cutting, but many books will not agree to this. So you have to be careful. They say that this is oblique cutting, but this is orthogonal, but I have earlier showed this also, that for if it is a orthogonal cutting, that means sin gamma p into tan alpha b will be equal to cos gamma p into tan alpha s. Gamma p is what? Principal cutting edge angle. That means in this case gamma p is equal to, suppose we say gamma p is equal to 90 degree, okay, because gamma p is side cutting edge is 0. So in this case tan alpha b, but this is 90, so tan alpha b 0. So that means in this case back rake angle should also be 0. That is also condition to be satisfied. That means you have to have, you can say first of all it should be tube machining only, so that cutting edge is extending beyond this one. Second thing is that there should be only the slope of the surface in this direction, there should not be any slope in this back this direction, okay. That means it should not be coming down, that means top rake should be 0. So this type of confusions is there, but you have to be careful. Now we find out forces, we do force analysis, we want to find out the forces, so we can consider force parallel to cutting velocity, that is active force, that basically machining, and we need to calculate it for finding out the power. Then there is a force normal to the machine surface, and then the force is normal to both. So force normal to machine surface like in the lathe machine you have, one is the cutting force that is tangential to the direction of motion, job is rotating and it is tangential to that. Then we have in the feed direction one force, and one force is of course in the radial direction also. Okay, that has to be this one, and we need to find out the forces for proper design of the our machine and process. Now, what are the assumptions in the analysis? Assumption is that tool is sharp and there is no rubbing or plowing action. Okay. Then stress distribution along shear plane is homogeneous, that is also we are assuming, and then resultant force from shear plane and rake face are linear, equal and opposite. This is also one assumption. Like in orthogonal cutting, we will say that there is a chip and the chip is supported from two sides by the forces. One set is applied by the rake surface, friction force and normal, and another is from the work material across the shear plane, and both are equal and opposite. But as we have already seen that these need not be equal and opposite, and that is why there is some chip curling is there. In fact, this concept is one thing that here you have, that assumption is there that these are linear, equal and opposite. And generally if we have oblique cutting with a single edge tool, then on the tool you get these type of forces, tangential and normal forces like this, and on the chip also you get the forces in other directions. And if we say the resultant of all the forces is R, then R can be resolved in two components. Suppose you have got a force, you know a particular force in 3D. If I have in Cartesian Euclidean system, then that force can be resolved into three components. One component will be called Fx, other is Fy and other is Fz. That you very well know that the force will have three components, but it is also possible to resolve the force into two orthogonal components, provided the force line is passing through a plane. So, for example, if you have, I make a cube type of thing, a box type of thing, and if I show that my one force is from this one to other diagonal cardinal point like this, naturally it has to be resolved in three components on all sides of this. But if I take a diagonal plane like this passing through this and this, then you can have only two components. This point has to be understood. So, component in a plane perpendicular to the cutting edge and component along the cutting edge I can take. So, then it can be resolved in two components also. And then Fp is the force along the cutting velocity vector, Fq is perpendicular to the work surface, and Fr is perpendicular to both P and Q as shown in this one next figure. So, resultant will be square root of Fp square plus Fq square plus Fr square, and same thing can be called as R dash square plus R double dash square. And if I take a rotated coordinate system, in that I can have this type of relation that can be done. Okay. Now, I am just, this is a figure from G.K. Ral's book of machining. In fact, Merchant has done this type of analysis for the first time. So, from that you observe that suppose we make different views. This is a rake face in which there is a chip is flowing in this direction. So, this is the force on the chip, rubbing force, friction force, but this is making eta c angle from here. This angle is 90 degree here, and this is eta c chip flow angle, which can be resolved. This force can be resolved into two components, that is F dash, and this can be F dash R. So, this is the rake face, and similarly other view is shown. Suppose tool is inclined like this and workpiece velocity direction is this. So, workpiece, so perpendicular, this is Fp, perpendicular to that it would have been Fr, but I am showing that perpendicular to this cutting edge. So, this becomes F dash P, that means angle between Fp and F dash P is I, and similarly this becomes F dash R, and this angle is I. Similarly, in the other view you can see Fq, and this is the tool, and you can see that velocity is in this direction. This is alpha n, and this becomes F dash S, shear velocity, and this is F dash n, and here we define that this angle as phi n and this is r dash. So, you can see that this angle becomes L phi n plus lambda n, where lambda n is the normal friction angle. Lambda n is defined with respect to that there is a F dash, that means if it is going F dash here and the normal force is n. So, ratio of this projected force to this will be called this one. Actually, true friction angle is basically F, tangential force is F, but this we can show it here, and then we can have here also this is eta S is also the shear angle in another plane. So, total force component Fp can be written as Fp dash cos I plus F r dash sin I, and if we put in terms of this one like orthogonal shear force in the shear plane inclined at an angle eta S to normal to cutting edge, that means it is inclined at an angle eta S to normal to cutting edge, and lambda n is the normal friction angle. So, like by Merchant's analysis type thing, you get this one Fs dash, but Fs dash itself is written as Fs times this one cos cosine I. So, it gives, so ultimately you are getting this type of relation, you can work out this, and lambda is the friction angle. So, in this case tan lambda n becomes F dash by n, but F dash is basically F times cos eta c chip flow angle. So, this becomes tan lambda into cos eta c. So, that means lambda n in this will be what? It will be slightly different from friction angle by this relation. Tan lambda n will be equal to tan lambda into cos eta c, where tan lambda is equal to F by n, and tan eta s will be basically F dash r divided by F dash s, that is here this one, and this can be written as F dash tan eta c and multiplied by this will be r dash cos phi n plus lambda n minus L phi n. So, tan eta s will be equal to tan eta c into sin lambda n divided by cos phi n plus lambda n minus L phi n. So, that means you will be getting this type of relation here and about this one. So, now here K is, if we consider K as the shear stress on the shear plane and As is the area of the shear plane, then Fs becomes equal to Kas. And what is As? As is the shear area. So, K is the shear yield shear stress of the material. So, this is K and this is Bt sin phi n, because B is the As. As is actually like this T by sin phi you used to do. Now, in this case it will become, thickness will become T by sin phi n, and B means width, that will be related by B by cos I. So, that means this is, so relationship that area As has become Bt sin phi n cos I, and it has become K times this one. And if we put these values from the previous one, Kbt, Fp is equal to Kbt sin phi n, and you will get this type of relation here from the previous relation. Okay, that means Fp is equal to F by F dash P. This relation is already there. In that you substitute and put that relation, you will be getting this type of relation, and Fq will be naturally equal to Fq dash. Okay, that in the figure you can see Fq is equal to F dash Q, that means this remains same, that perpendicular, that means vertical component type of thing, that you know this is along the reference plane. So, F dash Q is same, and then you will get this type of relation. Fq is equal to Fq dash is equal to R dash, and this becomes sin lambda n minus L phi n, and this can be written as F dash cos phi n plus lambda n minus L phi n, and this becomes F dash S is Fs cos eta c sin lambda n into this one, and substituting for Ns and Fs equation gives you ultimately by some algebraic manipulation, you get FR is equal to KBT sin phi n, and this you type of thing you get. So these are basically the force relations. They are given in your book of the GK Lal plus at many other places. So there is no issue, that expressions are well known, it is documented in the papers, but only thing is that you have to understand. So understanding is one. Similarly, you can obtain the velocity relations also. We are showing this diagram, this is tool, and in this one we are taking some section about that. Suppose VW is the velocity of this one, VW is the workpiece velocity, and VC is the velocity of the chip flow. If I take a plane which contains VW and VC both, then VW and Vs, that is CL velocity on the CL plane, that becomes Vs. Okay, like previous one, that there is a VW, suppose some job is moving on that, and on that it is sliding by Vs, that chip. So resultant velocity, it has become Vc, and this angle means the slope of this surface on this plane will be denoted by alpha e. That means how you will measure the slope. From VW you draw perpendicular, so that this is along reference plane, and from this angle is alpha e, that we have been calling as a two rake angle. And then here in this view they are showing the chip, and they have taken the section like this, and then this is a rake face, and they are illustrating that basically eta n, that in this chip flow in this plane on the normal plane, that this is eta n, and this is alpha n normal rake angle, this is Tc, and this is phi n here shown, phi n has been shown here, VW Vs, and this was basically I, and this one is here they are showing Vs, VW and Vs, and this is chip, and they are showing that on the CL plane there is B by cos I, this relation is also there. We will discuss about this in the next slide, that now we see in that diagram VW is the cutting velocity, or it can be the workpiece velocity, and Vc is the chip velocity in the rake face, and Vs is the CL velocity on the CL plane. Then you have got this type of relation like you have got in the Merchant's force diagram, that Vc is equal to V times sin phi e cos phi e minus alpha e, but now these values are two values, that means two rake angle. And similarly, if you resolve the components along x direction, then you get this type of relation, and then resolve along the y direction, you get this relation, and if you resolve along z direction, you are getting this type of relation. And solution of these equations, we can get Vc is equal to Vw sin phi n cos I and cos phi n minus alpha n cos eta c, and Vs is equal to, this will be cos alpha n cos I cos phi n minus alpha n cos eta c, and tan eta s is defined like this, tan I cos phi n minus alpha, tan eta c sin phi n divided by cos alpha n, and we can have CL angle relationship from here, and if we put that these values, in this case that tan eta c minus this one, some relation is there, then you get from geometry this type of relation. Now coefficient of friction mu, for that first you find out the f is equal to square root of Fp cos I plus Fr sin I sin alpha n, this quantity, and n is equal to this much, then mu becomes equal to tan lambda by F by n. And for shear strain and strain rate, you can find out this relation, Fs is equal to this type of expression, and Fn is equal to Fp cos I minus Fr sin I into sin phi n plus Fq cos phi n. And then the area of the CL plane is in fact As is equal to BT divided by cos I and sin phi n. I is the inclination angle and phi n is the shear angle in the normal plane. So shear stress is tau and normal stress is sigma. So tau is equal to Fs by As and sigma is equal to Fn by As, and gamma n is equal to is shear strain normal to the cutting edge. So that is basically delta S by delta Y. So this is as we have done in orthogonal cutting, and gamma is strain parallel to shear velocity Vs. Okay, so this one, so gamma is delta S by delta Y cos eta S. So gamma n is shear strain normal to the cutting edge, but this is strain parallel to the shear velocity. So both are related by this type of relation. So gamma is strain parallel to the shear velocity, and that is cot phi n plus tan phi n minus L phi n divided by cos eta S. And shear strain rate then can be found as this gamma dot is equal to delta S divided by delta Y cos eta S. This is 1 by delta T. Delta T is the time required for the metal to move the distance on the shear plane, this one. So these are relations I hope that you have understood, but don't get scared if you have not understood properly. These expressions are also you need not memorize. In exam, if somebody gives any problem, then he will give those expressions, and these you have to basically visualize. There are various ways to visualize. That means you can make the orthogonal views, or you can use 3D coordinate geometry. Then the things can become clear to you, and I will give that you will understand that how the forces are obtained. That is the derivation. Each of that work was one separate paper by various authors. Nowadays, of course, you are studying that in the books in 1 or 2 pages, but this is not so easy to understand also. And there, as I told, there is a controversy also that whether I should take the normal rake angle or true rake angle. These type of things are there. Now I am talking about something about that measurement of chip flow direction. That means how we are assuming that the chip is flowing. Chip in the orthogonal cutting is just flowing perpendicular to the cutting edge, but here it is not moving in that direction, it is inclined. So it is measurement of the chip flow can be classified into 2 categories. One is the indirect measurement and other is the direct measurement. So here indirect measurement, suppose you from figure you see that this one, it is a workpiece and this is the cutting edge. You see cutting edge is this and VW is this, workpiece velocity is in this direction. So this angle is basically I, and this is the rake face, and on the rake face I can draw one line which will be perpendicular to the cutting edge. So this is just perpendicular to the cutting edge on the rake face. Okay, that means the rake face, it is a that figure like this. So this is rake face, that this is 90, this one, and but your chip is flowing in this direction. So this angle is eta c on the rake face. Supposing it is going like this and this chip width comes out to B, then from this geometry, suppose this is eta c, then perpendicular to this will make eta c from here. So B by B, this is B, and this will be, suppose we say B divided by cos eta c. B divided by cos eta c will give us AB. Okay, so that means B, and here it will be, sorry, it is not B, here there is a mistake, here it should be BC. Okay, this is B. So suppose we say this BC from this diagram, BD by BC divided by cos eta c, that is equal to AB, right, isn't it? But here another diagram is giving me this angle is I. So what is happening that here AC is B, so B divided by cos I is equal to also AB. So equate both the things. So you divide B divided by BC, so So basically you get what? You get B by cos I is equal to BC by cos eta C. So that means B into cos eta C is equal to BC into cos I. B into cos eta C is equal to BC into cos I. So you get this type of relation, that B divided by BC is equal to cos I by cos eta C. Cos I is known to me because that is by geometry, inclination of the cutting edge, that you know at which angle you have set. You yourself have set it, so you know it. So this is cos I and this is cos eta C. So suppose you measure B and BC, then you can get idea about eta C. Stabler observed that most of the time it is basically eta C is almost same as I. In that case, B by BC will be same. That means chip width even in oblique cutting will remain same. Otherwise, in the later on he did some photographic study, and by that film study he found that eta C is in fact about 0.9 times I. So 0.9 times I means 90% of I, so cos I. So this value is cos I and this is cos 90% of I. So this is smaller. Smaller means this portion is bigger, that means B is bigger and BC becomes a bit B by BC. Okay, this is smaller, so B by BC is equal to, suppose I say cos I divided by cos 0.9 I. So that means this is suppose one value. So this whole thing will be, because cos 0.9 I will be more than cos I, because smaller the cosine angle, more it is. So that means this quantity is more, therefore this entire thing is less than 1. So that means B is less than BC. So that means there is some chip. So that means chip width may increase a bit. Okay, chip width may increase. Actually, we see that chip thickness also increases due to deformation, but the length reduces. But here it is showing that here BC is greater than B. So suppose BC is greater than B, that means the chip will also widen also a bit. That means it will spread also a bit. So that type of relation is there. From here you can obtain, and how you can measure it experimentally. So one method is that put very fine abrasive powder under the chip and you measure the angle of scratches produced under it. That type of thing can be done. Abrasive powder will scratch. Another method is involves staining the rake face of by Prussian blue and recording the mark. We can put Prussian blue on the top, and these methods are however not satisfactory, since the chip tool contact is over a very region, and fluctuations in a chip movement give false indications of chip flow direction. So that means it will basically, there can be chip flow fluctuation and you may have difficulty. Another method is that use of quick stop photography, as I have described in my previous lecture. Proper light source should be there, some fast film should be there, and method can be, nowadays today we have high speed cameras. These high speed cameras also can actually provide this thing, so they can give the recording and flow direction even at high cutting speed. So that is what this method records instantaneous and not average value, but you record instantaneous but you don't record average value. Now Stabler in 1955 proposed a relationship based on his experimental results, that eta C is equal to I, that chip flow angle is same as the I, and later he modified this as is equal to 0.9 I approximately, or sometimes between 0.9 to 1, and suggested that this correlates better with experimental data. Russell and Brown suggested that chip flow angle is influenced by the normal rake angle, and they proposed the following relationship: tan eta C is equal to cos phi n minus L phi n divided by sin phi n into tan I. So they have actually proposed this type of relation, that cos phi n minus L phi n divided by sin phi n tan I, and then incompressibility condition can be used to measure the shear angle. Now we know that LBT is equal to LC TC and chip thickness ratio RT is equal to T by TC, and that is BC LC divided by BL, and this BC by B can be written as BC by B is, suppose we write as RC, okay, RT is equal to T by TC, and then this LC by L, this will be BC by B can be written as cos eta C by cos I. Suppose you have got this one cos eta C by cos I. So here this will be T, and RT is equal to RC divided by this one. So if we say, if we define that chip length ratio as RC, RC is equal to L by LC. So this already I have done in this figure. Just remember this, B by BC is equal to cos I by cos eta C. So B by BC is equal to this one. So BC by B is cos eta C cos I. So this becomes RC and this becomes cos eta C and divided by cos I. So the chip length ratio is actually becoming L by LC, okay, that. And if we assume that basically eta C chip flow angle is same as the inclination angle, then we will be getting this type of relation from the previous relation. Suppose tan eta C is equal to tan I, then we get basically tan phi n plus L phi n is equal to cos L phi n divided by 1 minus sin L phi n. So from which we get actually phi n is equal to pi by 4 minus lambda n, and then you get and plus L phi n by 2. So this equation is basically similar to the shear angle relationship given for orthogonal cutting. That means automatically then you will get this type of relation. So that means if we believe in the Stabilus analysis, then in that case phi n will be actually equal to pi by 4 minus lambda n plus it will be alpha n by 2. So this type of relation will be coming and this will be done. So this much thing I have told about this one, and I will now just go back, draw your attention. If you want to really understand proper derivation, you have to understand each and everything very slowly. First of all, you see the observation that tan alpha n is equal to tan alpha v into cos I, because you are having some, if inclination is there, suppose you have something in the normal plane, in the orthogonal plane, that angle is going to increase here, and here sin alpha E is equal to sin I sin eta C cos I cos eta C into sin alpha n. Assume that one case in which supposing you say that I is equal to 0 and eta C is equal to 0. In that case this relationship gives nothing, but it gives that alpha E is equal to sin E alpha n. You can have another possibility also, that suppose you have inclination angle equal to 0, but your eta C is present, actually eta C is present. That means what is the situation here? That means this is a tool rake surface, maybe this is a tool rake surface, and tool velocity is like this is normal to that one, there no inclination is there, so it is like this, that this is the velocity type direction and this is the normal to that thing, but you are having this one eta C. You are having the eta C here, the chip is flowing like this. Now you want to say that I want to find out alpha E. That means basically when you are moving from here to here, that means you are moving here to here, how much is the slope of that surface. So this type of relation will give you sin alpha E is equal to here cosine I is 1, that means cos alpha cosine eta C and into sin alpha n, right. that means I am going to get this type of relation. Why? So can you derive this first? That means before moving to the complicated relation, first you can derive this one. And if we talk about cos eta c here, then cos eta c is basically this divided by this type of thing. Okay, cos eta c is, no sorry, this line divided by this, that is cos eta c, and this was sin alpha n. So sin alpha n will be measured here, that in the normal plane, and this will show the slope of that, and you can make use of the 3D coordinate geometry and you can visualize that. How do you measure sin alpha n? Suppose this is, you are at some vertical height and now your surface is sloping, that means surface is going towards opposite side. So that's why you are getting here alpha n. That means if some surface is just vertical, then there is no sin alpha n. So that means that will be, there is no slope, alpha n is 0, but surface is tilted. So that means this is this divided by this. Now same thing, if you are now going to in this particular direction, then you are moving, getting that some extra type of thing, that means sin alpha n is this vertical. So suppose vertical height is this, and this was that something diagonal height. So now this diagonal length has increased a bit. So sin alpha is equal to perpendicular divided by hypotenuse. So hypotenuse has increased by a factor of cos eta c. That is why you are getting cos eta c into this one. So that's why you are getting that this relation about this one. So that means sin alpha e is basically perpendicular divided by hypotenuse in that one plane, and this is cos, this is basically in that two plane, and cos eta c is cos eta c, that is again perpendicular and divided by hypotenuse in the normal plane. If I take the perpendicular same, then you can very well understand that there is a difference of this hypotenuse. So that means this slope. So this is something, these relationship you can properly do if you understand that my analogy when I told earlier slide also, that here if you are having some slope in that 3D plane like this, you have to visualize that what will be the slope of the surface. Slope of the surface is maximum in this direction, but in this direction it is 0, and in other direction you can find out the slope. In general, how do we find the slope of the surface? If I move from A point to B point, then if I know that how much I am moving vertically, that means this distance, and then I know this distance, then I can say that sin alpha, tan alpha is equal to this by this. Similarly, if I am moving, let us say, inclined way, so that means I have gone, say, let us say this point, and now I have gone inclined manner this thing. Na? So A to suppose B dash point. Now when I moved here to here, how much slope I encountered? So we can actually find out here also, we can draw perpendicular, we can join this one. So we can say there is a vertical height, I moved the same because height is h, but this now I traveled more distance in hypotenuse direction. So my sin will difference. Suppose here sin theta. So sin theta in this case was what? This was h divided by AB. But suppose I am moving from here A to B dash. In that case, my sin height was same h, but this will be AB dash. This was AB dash. So sin phi is equal to h by AB dash. So naturally AB dash is more. So that's why you will encounter that less amount of angle now. The slope will be less. So basically the same type of concept is there. If you try to visualize, if you see slides again and again, then you yourself you will understand, because it is a 3D, that is why it is very difficult to visualize. People make various type of models, but whatever best possible I have tried to explain through screens and 3D pictures. I hope that you will understand, and the next time we will talk other topics. Okay, thank you very much.